So what if I told you there's this hidden link between something as simple as pushing a box and something as chaotic as a car crash? Well, there is. Today, we're going to connect the idea of doing work with an object's energy of motion. And you'll see how this one single principle can solve some tricky physics problems in a really beautiful and simple way.
All right, our story actually starts with a bit of a puzzle. Way back in the 18th century, there was this brilliant scientist, Émilie du Châtelet, and she was doing these experiments, dropping lead balls into clay. And she noticed something really weird. When she doubled a ball's speed, you'd think it would sink twice as deep, right? Nope, it sank 4 times deeper. That just feels wrong, doesn't it? But trust me, figuring out why that happens is the key to everything we're about to unpack.
So, the secret to solving this puzzle isn't just about how hard the ball is hitting the clay. It's actually all about a concept called work. And yeah, I know what you're thinking, but in physics, that word means something very, very specific, much more than just, doing a job.
See, for a physicist, work needs 2 key ingredients. You need a force, and you need movement because of that force. Let me give you an example. Say you push against a solid brick wall for an entire hour. You're going to feel totally exhausted, right? But since that wall didn't budge an inch, you've actually done 0 scientific work on it. 0. So you really got to think of work as the act of transferring energy by actually making something move.
Okay, that seems simple enough. But, the real world is messy. We almost never have just one single force to think about. I mean, if you're pushing a box across the floor, sure, you have the force of your push, but you've also got friction fighting you every step of the way. So which forces work are we supposed to pay attention to?
And that brings us to a really neat shortcut. It's called network. Instead of getting bogged down calculating the work from every single force, we can just figure out the net force, the single overall force that's winning, and then calculate the work done by that. It's a lifesaver, and it tells us the total overall change in energy for that object.
All right, let's connect the dots here. How do we build a bridge from these ideas of force and work straight to an object's speed? This is where things get really cool.
Okay, so check this out. We're going to build something new right here. We start with our basic formula for network. Simple enough. Then we bring in a classic, Newton's second law, F equals ma. We use that to swap out net force for mass times acceleration. Still with me? Good. Next, we get a little fancy and replace acceleration using a standard kinematics formula that links it to speed. And now for the magic trick. When we put it all together and simplify, poof, the distance d just cancels right out. It's gone.
And this is what we're left with. It's such a clean, elegant equation, and it comes directly from just combining forces and motion. This, my friends, is called the work-energy theorem. And honestly, it's one of the most powerful tools you can have in your physics toolbox.
Now, this theorem isn't just some clever math trick. It's telling us something really profound. It says that the total work you do on an object is directly equal to the change in this very specific quantity, a quantity that's all about its motion. So what this theorem is really screaming at us is that work isn't just a number you calculate. Work is a direct transfer of energy. When you do positive net work on something, you are literally pumping it full of more energy.
In this special kind of energy, it's got a name, kinetic energy. Plain and simple, it's the energy an object has just because it's moving. Now look closely at that formula. The most important part to notice is that the speed v is squared. And believe me, that little squared symbol is a huge deal.
And this idea just simplifies everything so nicely. If you do positive net work, you're adding to its kinetic energy, and it speeds up. If you do negative net work, which is what friction does, you're taking away kinetic energy and it slows down. It's basically a perfect energy accounting system. Deposits and withdrawals. Okay, theory is great, but let's put this thing to work. Let's see how it solves that opening puzzle and tackles a real-world problem. This is where the math on the page becomes a seriously powerful tool. Remember how I said that v squared part was a big deal? Here's why. The relationship isn't 1-to-1. If you double a car's speed, say from 50 to 100 kilometers per hour, you don't just double its energy, you quadruple it, 4 times the energy. That right there is why high-speed collisions are so incredibly destructive. And it perfectly explains Émilie du Châtelet's experiment. Twice the speed meant 4 times the energy to push that clay out of the way. Puzzle solved. All right, let's try a hands-on example. We've got this package on a conveyor belt. We want to figure out its final speed after we give it a good push. And here's the cool part. Using the work-energy theorem, we can find that speed without ever having to calculate acceleration or time. We're just going to follow the energy. Okay, step 1. Let's find out how much energy we're starting with. We just grab our kinetic energy formula, plug in the package's mass and its initial speed, and boom, we get a starting energy of 3.75 joules.
All right, now it's time to change that energy. We're going to do some work on this package. We're pushing it with a force of 120 newtons, but friction is pushing back with 5 newtons. So the net force, the overall force, is 115 newtons in the direction we're pushing.
Okay, so we push with that net force for a distance of 0.8 meters. The work we've done? It's just that force multiplied by that distance, which gives us 92 joules. So think about it like this. We have just injected 92 joules of brand new energy into that package.
And here comes the beautifully simple part. The work-energy theorem tells us the final energy is just the energy we started with plus the work we put in. That's it. It's just simple addition.
So let's do the math. We take its starting energy of 3.75 joules, we add the 92 joules of work we just did, and the package's new grand total of energy is 95.75 joules.
Okay, we've got the final energy, which is great, but the original question was about the final speed. No problem. We just take our kinetic energy formula again, but this time we do a little algebra to solve for V.
And there it is, our answer. We plug in our final energy and the mass, run the numbers, and we get a final speed of 2.53 meters per second. And I want you to notice something really important. We never once had to calculate acceleration. We got the final speed just by tracking the energy. How cool is that?
This little example really shows why thinking in terms of energy is often so much more powerful and, frankly, more direct than just using forces and kinematics on their own. It lets us jump over all those intermediate steps like finding acceleration in time. We get to connect the cause, the network done, directly to the effect, the change in kinetic energy.
So when you boil it all down, the big idea today is that work is simply a way to transfer energy. But that leaves us with one last nagging question. Remember the friction? It did negative work, which means it took energy out of the package's motion. But we all know energy can't be created or destroyed. So where did that energy go? That's a fantastic question for another time.